Hello everyone, my name is Kathan and today we'll be discussing the problem Distinct Values Subarrays II from the sorting and searching problems of the CSES problem set. Let's begin. Let me read out the question for you. Given an array of n integers, your task is to calculate the number of subarrays that have at most k distinct values. If you remember, the distinct value subarray is one question. We had to calculate number of subarrays with distinct values. So here we have to find the number of subarrays that have at most k distinct values. In simple words, now duplicates are allowed in subarrays. It's just the distinct count cannot go beyond k. Okay, fine. The input. You have first line has n and k, n representing the size of array and k representing the maximum allowed distinct values in a subarray. Output, print one integer number of subarrays, or you can say the valid subarrays here. That is number of subarrays with k distinct elements. So we discussed the example test case and constraints on the iPad, but I guess the question is clear. Before we go on to the discussion, I highly suggest that you watch the distinct value subarrays 1 video, or at least know the optimal approach, right? The sliding window based approach that we discussed in that video, because this question will again reuse a lot of ideas that have been discussed there. So it would be a great thing. Even if you don't watch it, it's fine, but there might be a disconnect if you don't watch that video or you don't know that approach. Fine. So let's move on to the iPad and discuss this question a bit more. First things first, let's talk about constraints here. So n is as high as 10 power 5 and k is less than equals to n. Now what does this say? If you try to implement order of n square solution, it's gonna consume 10 power 10 operations. But you know that in 1 second you cannot do more than 10 power 8 operations. So n square is out of the picture. So then you'll have to do n log n, right? N log n or something better than that. Now let's try to understand this question using an example test case. So n was 5 and k is 2. So what does k equals to 2 means? You find me all the subarrays, find all subarrays with at most is important, right? Not exactly, at most k distinct values, or you can say at most 2 distinct values. That is 1 distinct value is allowed, 2 distinct values are allowed. Okay. So that's one thing. 0 distinct values is not possible because we are not considering empty subarrays. It is clear from that question. Now the array was 1, 2, 3, 1 and 1. Now you want to find out here all the subarrays that have at most 2 distinct values. And how does those subarrays look? Let's see. So what we'll do is we'll try to find subarrays ending at every possible index to find out. Okay. So what are all the possible subarrays ending at this index, which has at most 2 distinct values? So there is this one guy. So the count here is 1, right? The number of subarrays ending at index 1, if I write the indices here, 1, 2, 3, 4, 5, ending at index 1 is simply 1. Okay, fine. Let's try to find all the subarrays ending at index 2 with at most 2 distinct values. So one subarray is this. This subarray has only 1 distinct value, which is fine, which is allowed. So the distinct value allowed are 0, like 1 and 2. Right? 0 is allowed, but it's fine. We don't have empty subarray, right? So maximum we can have 2 distinct elements. 1 distinct element also work. Fine. So 2 here is the answer. Okay. Then what other subarray you have? This subarray, right? So there are 2 subarrays ending at index 2 with at most 2 distinct values. So yeah, we have, you can say the contribution at this index. So number of valid subarrays ending at this index is 2. Okay, fine. Let's talk about index 3. Now once we have this subarray has 2 distinct elements. This subarray also has 2 distinct elements, but we cannot have these distinct elements. So we cannot have this, right? So we cannot have this subarray, right? So if we don't know the number of subarrays ending at a given index j is simply j if we are using 1 based indexing. Right, so this I guess we have discussed a lot of times, so I'll not go too deep into it. Fine. So that's one thing. So here again the contribution is 2. Okay. Now let's try to find the subarrays ending at index 4 with at most 2 distinct values. Now one subarray is this, another subarray is this. Right. So again there is only 2 contribution, right? Because these 2 subarrays cannot be included. So all in all, the maximum subarrays ending at this index 4 were 4, but only 2 of them have at most 2 distinct values. So again, the contribution here is 2. Fine. Now let's talk about the guy at index 5. Now one subarray is this, one subarray is this, one subarray is this. So here we still have only 2 distinct values, right? And yeah, these 3. So if you try to include one more or any more, we'll have more than 2 distinct values, which is not allowed. So here the contribution is 3. So all in all, how many subarrays are there, guys, which have at most 2 distinct values? So you just add the contribution of every possible index. So 1 plus 2, so like this is 6 plus 3, 9 plus 10. So 10 is the answer. So that's what you have to print. They don't ask us the actual subarrays, they ask us the count. So that's what you have to do. Fine. Okay. So the question is clear, right? Now how do you approach this question then? Like, so brute force is obvious. You just enumerate all the possible subarrays, right? You enumerate subarrays at ending at every possible index, which will be what? Order of n square. Because you know that the number of subarrays ending at index 1 is 1, ending at index 2 is 2, ending at index 3 is 3, so on till n. This is sum of first and natural numbers. So it turns out to be order of n square, nn plus 1 by 2, right? So brute force is not going to work, but if brute force is not going to work, then let's think if we can find the contribution of every possible index optimally, right? Because that's the recurrent, you can say recurring theme for subarray based questions. So what I'm saying is, can we count number of subarrays with at most k distinct elements ending at j belongs to 1 to n in optimal time. If I can do that, then there are only order of n subproblems here, right? Because j goes from 1 to n. And if I can count the number of subarrays, you can, let's just call them valid subarrays, right? So valid subarray means a subarray which has at most k distinct elements. If I can count the valid subarrays ending at a given index in optimal time, I know there are order of n subproblems, and this can be done in optimal manner, let's say some log n or something. We have a efficient solution, right? Okay, so this we can do. So how can this be done? But if you recall, a lot of questions in this playlist, like the playlist question and distinct value subarrays question. If I want to find like what is the count, you can say, of valid subarrays ending at a given index j, what can I do? See, I want to maximize the count. I don't want to leave out any subarray which has at most k distinct elements, right? So what can you do is, you find me the smallest I from the left, such that I to j has less than equals to k distinct elements, right? It has no more than k elements. That's what I'm saying, right? And if you can find me this window, I know for the fact that in this window I don't have more than k elements, right? You find me the smallest I from the left for every j, such that in this window we don't have, you can say, the unique element count is less than equals to k, that it doesn't exceed k. Then I can add the contribution of all the subarrays in this window. And do you know how to calculate the contribution of a window? I guess you already know. If you have, let's say, some elements here, 4 elements, whatever the index are, let's say I till j. If you have 4 elements, what are all the possible subarrays? First is this. All in all, if you have 4 elements, the number of subarrays contributed by this window are 4. In other words, the number of subarrays contributed to the window is how many number of elements you have, that is j minus I plus 1. I'll repeat myself again. So I'm going a bit fast here because we have discussed this strategy a lot of times. But okay, I'll come again. See, what we want to do is we want to find the number of valid subarrays ending at a given index j. What constraint do we have, guys? Our subarray cannot have more than k distinct elements. Okay, so it might happen that if you consider all the elements from the start, there might be more than k distinct elements, but we are not supposed to be having more than k. Like we're not supposed to be having more than k distinct elements. So what I'll do is, you find the smallest I from the left, such that we don't have more than k distinct elements. So we have less than equals to k distinct elements. Smallest I. So smallest I will ensure we don't miss out any subarray, right? And the number of array elements are no more than, distinct array elements are no more than less than equals to k. And once you have this I, the contribution of this j is simply j minus I plus 1, which is nothing but number of elements you have in this window. Right, so let's do a dry run of this strategy. We have discussed this strategy a lot of times, but who knows, maybe you are watching this video for the first time. So let's do a dry run and you'll get this strategy. This strategy is actually very simple, and a dry run will actually clarify everything. So dry run on the same example, right? So 1 2 3 1 1. So the index were 1 2 3 4 and 5, right? So initially I and j both are 1. So initially we are starting our journey, we are starting our contribution with the first guy, right? We want the contribution from every possible index, right? We want to find out the valid subarrays ending at every possible index. What is valid? Subarray which has at most k distinct elements. So in this question k was 2, right? So maybe let me write k here. K was 2. Okay, fine. So I'll initialize one more thing. I'll initialize my answer, which is my subarray count, and now let's start our journey. So we'll need one more thing to keep track of, you can say, the window elements. We will need a map. Why map? You will see in a bit. So we start our journey from I equals to 1 and j equals to 1. I guess I'm hiding that k. Maybe let me write it. Alright, let's start our journey then. So we start from the first guy. So add this element into the map. So let me write the map here on the right hand side. So we have 1 present 1 time. Okay, you have present 1 time. Now what do you check in your window? Do you have more than k elements? Do you have more than k elements? No, in your window you only have 1 element. Okay, so simply add the contribution for all the elements in this window. So you only have 1 guy, so we will just simply add 1, right? So in answer we add 1. Okay, fine. Now move j ahead. So j now comes here. Okay, now when j comes here, now you add j, you can say add the element into the window. So now 2 also occurs 1 time. Okay, now when you add the element to the window, do you have more than k elements in the window? So what is the window, guys? The window is this. So window is this. Do you have more than k elements in the window? No, you don't have more than k in the window. So simply add the contribution of all the elements in the window. That is, this will actually give you the count of all the subarrays, valid subarrays ending in index 2. So which is nothing but j minus I plus 1. So you simply add 2. Okay, fine. So now j moves ahead. So when j moves ahead, you add 3 into the window. Now as soon as you added 3 into the window, now your window size has increased, right? You can say, in other words, your map size has gone beyond k. If this is the case, we have to shrink the window from left. We have to find the smallest I from the left, such that we have at most k unique elements. So shrink the window from left. That is increment I. Increment I means this one is gone. Now you stop. You move it just enough such that you have k distinct elements. So now in this window again, you have at most k distinct elements. Now you add the contribution, which is again simply 2, j minus I plus 1. So 1 plus 2, maybe let me write below. Again 2. Now j moves ahead. Now when j moves ahead, again 1 is added into the window. 1 is occurring 1 time. 1 is added into the window. Now, is the map size greater than k? Yes, definitely. So shrink the window from left just enough such that I to j have unique elements. So we shrink the window, so 2 is gone, and now we have a window of which has at most k unique elements. So add the contribution. So contribution is j minus I plus 1, or the number of unique elements you have. Okay, plus 2. Okay, now we move j ahead. So now when you move j ahead, only once frequency will change, right? No new element is added. Now, is the map size greater than k? No. So there is no need to shrink the window. Now add the contribution of this window. That is, add the contribution of this index j. So what are all the possible subarrays ending at index 5? Valid subarrays, right? Which has no more than 2 distinct elements. 1, 2, 3. So we just add 3 to it. Right, and then j goes out of bounds. And we have our answer. So this answer is nothing but 10. Right? So, I mean, yeah, that's the strategy. And if you see what is the time complexity here, effectively what has happened here is I and j are moving one time from left end to the right end of the array. So the time complexity here you can say is order of n. And then there are some map operations, right? So if map size has become greater than k, then we are removing elements from the map, right? So reducing the frequencies and all. So definitely order of n into map operations, which are nothing but log n, right? So time complexity is n log n. N reason being I and j are moving at most once from left end to the right end of the array, and log n being the of the map operations. Space complexity is of map. In the worst case, we may have to store all the elements in the map. So space complexity is order of n. So yeah, I mean that's the approach, guys. So I hope you have understood the approach. If you did, please comment understood in the comment section of the video, and let's move on to the code and wrap up this video. Alright, guys. So here's the code. First things first, I'm taking the array input, right? So n, size of array, k, the maximum allowed distinct values, and the array itself. Fine. Then I'll need a map to keep track of unique count. So how many unique elements are present in the current window? So answer being the total number of subarrays, and I equals, so we start a journey, right? So these are I and j are my window bounds. So while j greater than n, j is less than n. So while we have taken contribution from every possible index. So here it is 0 based indexing. So we are going from 0 to n. Then we add this guy into the window, add current guy into the window. Now we shrink the window until we have at most k unique elements in the, you can say, in my window I to j. So while length of map, so this length is not a standard C++ function, we have a type defined here. And while the length of map is greater than k, while we have greater than k unique elements in our window, we first reduce its frequency. If that element is frequency becomes 0, we remove it. So we basically shrink the window and I++, right? And now when this loop ends, I'm sure that in my window, in that is the array of I till j, I have at most k unique elements. So add its contribution, which is j minus I+1. Notice I'm not doing here map size, right? Because the number of elements may not be equal to map size, right? Because the number of elements here are not unique. So map only stores unique elements. So j minus I+1 is the way you should calculate the number of elements you have inside a window, right? Length of map may not store the, you can say, number of elements. You just saw it, right? So if you had elements like 1, 1, 3 in the map, it will be like 1 is occurring 2 times and 3 is occurring 1 time. But j minus I+1 will, you can say, consider the case, you can say, we'll consider that, right? So it will be actually 3 only, the bounds. So if you want to add the contribution of given index j, you simply do j minus I+1 and we move j ahead. And after this loop ends, we have taken contribution for every possible index. And time complexity, I guess we have already discussed, n log n, space complexity order of n. And yeah, and we just print the answer in the end. So yeah, that was the video, guys. I hope you liked it. If you did find it helpful, please give it a thumbs up, and I'll see you in the next one.